So in this video, we're going to be going over our very first project, which is the bisection method, and what is, I think, a very good introduction to the course. So first off, I wanted to go over conceptually, what is the bisection method? What are we trying to do here, and what are we trying to accomplish within MATLAB? And well, it turns out it's really simple. All the bisection method does is it finds the root, or the zero of a function. And so, if you were to imagine me giving you some sort of function, let's call it f of x, and let's make it some sort of line. Well, if I gave you this function explicitly, this would be very easy for you to solve, right? It would just be some simple algebra. Well, the tricky part comes is when we try and get a computer to do this same task. Not necessarily just for line functions, but for even more complex functions. And that's where the bisection method comes in. All it is it's an algorithm or a stepwise function in order to accomplish this same task. So, in order to understand the bisection method, I'm going to redraw this graph, and I'm going to make the function's behavior a bit more arbitrary. So I might just do whatever I want. I might go do anything, but eventually it will cross the x-axis, and we're trying to search for this root. And so before we can even start the bisection method, we have to come up with three parameters. The first of which is a, and that's the left bound of the interval we're trying to search for the root over. I'm going to put a right here. A. And then the next parameter is b. And as you might guess, that's the right bound of the interval we're trying to search for the root over. And so this idea of an interval and bounds might seem familiar to some of you. This is similar to when you use your TI-84 to find the root of a function. You set your left bound and your right bound, and the calculator searches over the interval to find that root. I'm not completely sure if the calculator uses the bisection method in order to accomplish it, but the algorithm must be similar in the fact that, again, we're using this idea of bounds in an interval. So we have our first two parameters, a and b. The final one is tol, or tolerance. And tolerance is some value that's close to 0. And what tolerance does is it basically tells us when we can quit out of the algorithm. Because we can keep going and doing the bisection algorithm over and over and over to get greater and greater accuracy as to what this root really is, but that just wouldn't be realistically feasible, because if we wanted an infinite amount of accuracy, it would take an infinite amount of time to get that. So tolerance is just some value close to 0. So essentially, when we find a function value that's really close to 0, we can just quit out because we found something that's close enough to the root for our given purposes. So within this project, I believe we use 1/100th. So when we find an x value whose function value is 1/100th or less, we know we can quit out because we've essentially found the root. So now we have our three parameters. So we can actually go on to the steps of the bisection method. So the very first step we check is this. Is f of a times f of b less than 0? So what is this step and why are we doing it? Well, if you can see here, we're trying to see if whatever f of a is times whatever f of b is, if that result is a negative number. And as you can see here in this example, it is, because f of a is a positive number, and f of b is a negative number. But what this line is really checking is that over this interval, are we switching from positive numbers to negative numbers? Because if this is a continuous function across this interval, if we switch from positive to negative numbers, we know that we cross the x-axis, and there must exist a root across this interval. So all this very first line is doing is it's verifying that we have a root across the interval. And so, if this line wasn't to pass, we can just quit out early, because there's no guarantee that a root lies across the interval. So there's our first step. Then, what's the next thing we do? Well, as the name implies, we bisect the interval. So we bisect. I'm going to take this interval, divide it right in half. I'm going to call it x. But how do we represent x mathematically? Well, it's just a simple average. What we're going to do is we're going to take the average of a and b to get right down the middle. A plus b. Good. So now we've bisected the interval. So the next thing we're going to do is we're going to open up a while loop, because we're going to need to do this bisection method a few times, because our ultimate goal is to center this x value right on the root. So we're going to have to move this x a few times around. And a good way to do that is to use a while loop. So we're going to do this. While the absolute value of f of x is less than tolerance. So what is this line telling us? This line is saying, well, we have a function value for x that's still bigger than our value that we said we could quit out on. We have to keep going through a bunch of steps. We have to keep moving this x value around until eventually we get a function value that's smaller than tolerance. And only when we found a value that's smaller than tolerance have we found that root, and we can finally be done. So then within this while loop, we create an if statement. We check, is f of a times f of x less than 0? And so this line is actually similar to the very first line. In this very first line, we're checking if the root exists across the entire interval. This line is similar, except we're only checking this half interval from a to x. So again, see if we switch over from positive to negative values or negative to positive values. And so if this ends up being true, what we do is we set b to be equal to x, and we bisect again. So good. We can check the left half of the interval. But if this fails, then we move to an else statement, and then we check the right half interval. So then we do f of b times f of x. Is that less than 0? And so we're checking the right half of the interval. Again, this line is similar to this line, is similar to this line. It's checking to see if it crosses over the x-axis and if a root exists across that half interval. And so then if this one ends up being true, we set a to be equal to x, and we bisect again. Good. And so this is the entirety of the bisection method. And what the real bulk is these few lines. Because we're going to keep repeating these lines until eventually we move x to be in such a place that it's less than tolerance. So now that you've seen the algorithm, let's run through it using this example in order to see the flow of it. So the very first line, we check, is f of a times f of b less than 0? Positive number, negative number. All right, we're good to go. We don't have to quit out early. So then we bisect it using that average. Right? And I've already done that. Now we check this statement. Is the absolute value of f of x less than tolerance? Well, f of x is still a large value, so we're going to have to go into this body of this while loop and continue moving on. So then we check the left half of the interval. Is f of a times f of x less than 0? F of a is positive, f of x is positive, so nope. We're going to skip this and then skip the line underneath it. Then we move to this else if. Is f of b times f of x less than 0? F of b is negative, f of x is positive. Yes. So what we're going to do is we're going to set a to be equal to x, and we're going to divide. So then this one goes away. And this is our new a. And then we bisect. X. All right, then we go back up to the top again. We check. Is f of x less than tolerance? Well, nope. F of x is now a slightly negative number, so this line isn't going to pass, and even with the absolute value, it's still greater than our tolerance. So this doesn't pass, so we have to go through again. Then we check again. Is f of a times f of x less than 0? F of x is negative, f of a is positive. Yep, so we're going this side now. So we set b equal to x, and x is equal to a plus b over 2. We bisect again. This is b, and this is x. All right, and then we cycle back up to the top of the while loop. And we check one last time. Is the absolute value of f of x less than tolerance? In this case, yes. It's very close to tolerance. So now we finally found an x value that's good enough for our root, and we can quit out of the algorithm. We found the correct x. So that's the entirety of the bisection method. We're just repeating these steps, and we're going to repeat these steps mainly over and over again until we center this x value on the root we want. So now that we've seen conceptually what the bisection method is, I want to go over what you need to do in this week's project. And it actually turns out to be really simple. What you're doing is something called bar cooling. So we're just going to be modeling the cooling of a bar using some sinusoid function, and we're going to apply the bisection method to that sinusoid function. So I believe the sinusoid function is called cool fun. And it varies on two parameters. First being x, which is this variable of the function, and then we have this constant L, which you're going to multiply in somewhere to that sinusoid. And so what you're going to do is you're going to do the bisection method on cool fun for various L values. So in total, I think you're going to get approximately 30 L values, so 30 different cool fun functions, and you're going to apply the bisection method to each of those sine functions and get out whatever the root is, whatever x is. And so what you're going to end up having is a matrix of all the L values and a matrix of the same size of all the x values, because you're only going to be finding a single one of those sine roots. So then you're going to have two equal matrices, or two equal size matrices. And what you're going to end up doing is you're going to plot L versus x squared. And so that's all this week's project is. All you're doing is you're taking a sine function, bisecting it, and then you're making a fancy looking graph. And so obviously the most challenging part of this project is actually going to be writing the bisection algorithm. But again, a lot of the code is included within this first project, so just look within the project documentation. But of course, if you still need additional help, come talk to me, text me, come to office hours, and we can get it sorted out. I hope this one helps, and I'll see you guys in the next one.